Though the formation of the equations was completed, it wasn't exactly clear that they would necessarily model turbulence. Thus was another question at the time. After all, there's still today no analytical solutions on the Navier-Stokes equations for a turbulent flow, an analytical one at least. So this is also a separate development, but interrelated. Osborne Reynolds, for a long time, was only seeing, among others, the Navier-Stokes equations to only describe laminar flows and not turbulent flows. And this is a whole other discussion, but it's worth looking at. Is what is turbulence? Leonardo da Vinci used the term turbulenza and wrote, where the turbulence of water is generated, where the turbulence of water maintains for long, where the turbulence of water comes to rest. This term turbulent was actually coined by Thomson, otherwise known as Lord Kelvin, in 1887, which isn't that long ago, in a paper called On the Propagation of Laminar Motion Through a Turbulently Moving and Viscid Flow. Navier called the flows linear and nonlinear flows, which makes a lot of sense mathematically because, well, one gets rid of the nonlinear term, for example, then the flows can't be turbulent. Reynolds called them direct or sinuous flows, and I think this makes sense because of his fundamental experiments in a channel where he developed the concept of Reynolds number and instability, that the instability looked sinuous. Oseen called turbulent flows where the Navier-Stokes equations blow up. He was more of a mathematician and developed Oseen solutions, which I'll mention later. We all know that Reynolds experimentally studied turbulent flows, but he wrote, the internal motion of water assumes one or other of two broadly distinguishable forms. Either the elements of the fluid follow one another along lines of motion, which lead to the most direct manner to their destination, or they eddy about in as sinuous paths, the most indirect possible. In 1895, Osborne Reynolds introduced the time averaging, or what we call Reynolds averaging, where we decompose a variable into its base plus its fluctuations. The left-hand side is, say, the velocity. The first term on the right is the time average, and the final term is the fluctuating term with the prime. More mathematicians followed, and Lorentz in 1896 re-looked at Stokes' steady creeping flows. He looked at a sphere with radius r and velocity c and let r approach 0. He found that there's a Green's function for steady Stokes flow. This is called the so-called Stokelet or Oseen tensor. One can use Green's functions then to write more general solution for Stokes flow. Oseen in 1911 extended the work of Lorentz to the case of evolutionary Stokes equations, and then to the Navier-Stokes equations, and found a tensor, the Oseen tensor, such that the Stokes equations can be written this way with a closed-form solution. This is that Oseen tensor, which is basically like a Green's function for the problem defined by Lorentz. For incompressible Navier-Stokes, we can write the closed-form solution as an integral differential equation in equation 9 like this. You'll see that this is indeed a closed-form analytical solution for the velocity field in the incompressible flow without the nonlinear term. W sub nu is the heat kernel associated with this Green's function. So it's the Green's function of the heat equation in an infinite space. And of course, this Oseen tensor is also defined for an infinite space. One could go and seek tailored forms of the Oseen tensor and the heat equation Green's function and construct tailored velocity fields. They're dependent on velocity and time. But remember, there's no nonlinear term. So this would be for a nice creeping laminar type flow. There's nothing in here that states about like the boundedness of velocity or anything. Anyway, it's very possible for a solution to be found for small time intervals when the initial data and forces in the flow, initial data, are regular. A little later, in 1934, Leray examined the turbulent solutions on Oseen's approach when the estimates of Oseen blow up. So if we take this equation and we look for blow up, you say, well, maybe the flow is unstable and becomes turbulent. He showed that one had to estimate that it did not blow up based on the NT norm of the energy. So energy was being tracked in the equations, but remember, energy is not a coupled equation in the incompressible equations of motion. There's no first law of thermodynamics yet. We're looking at blow-up of energy. Anyway, Leray introduced the concept of the so-called weak solutions. They're turbulent solutions, if you will, but they're weak, for which the derivatives in the differential equations were no longer classical derivatives, but generalized derivatives. He defined a space of functions that live in measurable square integral and have a generalized square integral gradient, and would be called the Sobolev spaces, H1. So this is our definition. Leray proved that Ossine's classical solutions could be extended to global turbulent solutions. But their physical meaning might be suspect because we've already said that the nonlinear term is negligible, or zero. Nonetheless, we call these types of solutions the weak solutions. And Leray showed that these solutions existed through compactness arguments. A number of years later, these methods opened the questions of uniqueness of the solutions to the whole Cauchy initial value problem. Uniqueness of weak solutions, or of globalness as we call them, of strong solutions has remained an open problem since Leray's thesis. Leray constructed weak solutions using the formulations derived by Lorentz and Ossine for the hydrodynamic potential equations. These formulas were explicitly known only for very simple domains and not available for complex domains. Alternative approaches were developed in the 1950s by Huff and Navier-Stokes, both famous mathematicians of our time. Equations were approximated in finite dimensional subspaces, or the so-called Fado-Galerkin method. In the 1960s, Navier-Stokes created a theory for the use of these weak solutions for partial differential equations in hyperbolic fields.